All right, students, today I'm going to show you some example problems from our Unit 6 worksheet number 1. I am going to let you know that I've changed all the numbers on these. So if you're a student or another teacher, just be aware that I've changed all the values in these so that these only are demonstration problems. They're likely not what you've given to your students, unless, of course, you happen to choose the same numbers that I did when I replaced them in these problems. These look a lot like well, they're exactly like the problems I gave my students, but all the values are changed. So I want to give you a heads up about that. If you see these exact answers show up on your students' work, then that's probably because they watched my video and not because they were paying attention and did the work themselves. So I just want to put that disclaimer up on the front that if you're concerned about students copying these and then turning them in, they're not going to have any of the right answers if they just copy them. These are just example problems for students to do. My name is Dr. Christina O'Malley. This is Better Science Teaching. I'm also a licensed 7 through 12 science teacher in the state of Ohio. And I'm posting these to YouTube as many other teachers are posting things these days to help my students while we're trying to learn from home. I don't get quite as much time with them as I used to. We only are working about 30 minutes a day online, and they can't just pop in and ask questions during study hall or before or after school. So I wanted to give them some ways that they could asynchronously, outside of our regular meeting times, be able to take a look at homework problems and samples and see if that was something that could help them. So this is our unit number 6, which I call Projectiles, but is also called the 2D particle model. And this worksheet is, as you can see, free fall kinematics. So let's get started. A baseball is thrown downward after reaching an initial speed of 15 meters per second on Earth. Make a labeled diagram, specify the positive direction, and then make a motion map of the situation. So this is a baseball that's being thrown down towards the ground. In my class, I like to have up be the positive direction and down be the negative direction. And we've got a baseball that's thrown downwards with an initial velocity of minus 15 meters per second. It's negative because it's going in the negative direction, and this is a vector. Next question says, what's the acceleration? Let me go back. And then make a motion map of the situation. So we know that at time equals 0, we have an object that's being thrown downwards. And in the first second, it's going to travel 15 meters. So I can put a little bit more detail in here. Here's 0 meters, here's 15 meters, and that's downward travel again, so it's negative. After the next one, it's going to have accelerated in that direction another 10 meters per second. So it's going to be traveling an additional 25 meters. So it's going to have reached a distance of 40 meters as it's traveling. And then, as we do with motion maps, we draw arrows that are halfway the distance between those two dots. This isn't a very big motion map, but it'll get us started. The next question says, what's the acceleration of the ball? Well, it's the acceleration due to gravity. And I allow my students to use minus 10 meters per second squared. It allows the calculations to be a little bit simpler, and we only lose about 2% of accuracy because of not using 9.8. Next, we have to do a calculation. So we know 2 things so far. We know that our initial velocity is equal to minus 15 meters per second, and we know that our acceleration due to gravity is minus 10 meters per second squared. We're asked to calculate the displacement, which is our delta y, our change in our vertical position in the first 5 seconds. Okay, so it turns out there's an equation we can use to solve that. Whenever we have 3 things that we know, we can always solve for the missing variable. So I have on a post-it note all of my equations because it keeps them handy. But here we need something that's got our change in vertical displacement, initial velocity, acceleration, and time. So I'm going to use the second one here, this quadratic. So our change in y is equal to 1/2 a t squared plus initial velocity times time. So we know all these values, so we can fill these in. Minus 10 meters per second squared times 5 seconds squared plus our initial velocity minus 15 meters per second times 5 seconds. If we put those into a calculator, we find that what we have is minus 125 meters, so 125 meters down for this first section, plus another minus 25 meters for the second part of our equation. So this change in position then is going to be minus 200 meters. I'm not sure where this baseball player was standing that he could throw something downward 200 meters, but he did it. Next, calculate the time. So now we're going to find time required to reach a speed of 45 meters per second. So now we're given a new final velocity. So our final velocity equals 45 meters per second, and it doesn't specify which direction, but I'm going to assume that it means downwards because we don't have anything that's indicating that this ball is going to change direction. So I'm going to say minus 45 meters per second. We know that we had an initial velocity of minus 15 meters per second, and our acceleration still is minus 10 meters per second squared. I apologize for that. This is my first video. Okay, so we've got our unknown. We're trying to find time. We know final velocity is minus 45 meters per second. Initial velocity is minus 15. Acceleration is minus 10 meters per second squared. So again, we have three things. We're going to solve for the missing one. This again is vertical motion. So the equation that we are going to use is this first one. Final velocity equals initial velocity plus acceleration times time, and we're going to solve for time. So our initial velocity minus 15 meters per second plus our acceleration minus 10 meters per second squared times the amount of time, which is what we're trying to solve for. Let's see. There we go. So the first thing we're going to do is add 15 to both sides. So we will have minus 30 meters per second on one side, minus 10 meters per second squared times time on the other side. And then to solve for time, what we need to do is 30 meters per second divided by minus 10 meters per second squared. And that gives us a time of 3 seconds. Now you'll notice if you look at this, we could rewrite this in a different way by rearranging this equation. So if we just rearranged this equation to solve for time, we could do that with time equals final velocity minus initial velocity divided by acceleration. My personal preference is to keep things simple. If we only have to remember 4 equations, that's a lot easier than remembering all these different rearrangements of equations, which is all that really is happening in physics. But this would lead us to the same thing. 45 minus 15, give us minus 30, divided by the acceleration due to gravity, and that would give us our time. Next, calculate the time required. So we're going to solve for time again. To fall 200 meters. So if we're going to fall 200 meters, we're going to go 200 meters down. So that's going to be a negative number. So our change in vertical position is going to be minus 200 meters. Our initial velocity remains minus 15 meters per second. And our acceleration due to gravity is minus 10 meters per second squared. So now we need to solve this for time. Okay, this is factor the quadratic. Guys, this is a tip. If you see that pop up on your assignment, that means you're using this equation. All right, so our change in y equals 1/2 at squared plus vit. And then we fill in our numbers. Minus 200 meters. I don't want to forget my units. Minus 200 meters equals 1/2 times minus 10 meters per second squared times time squared, which is our variable, that's what we're trying to find, plus minus 15 meters per second times time. So if you remember how to do quadratic equations from algebra class, 0 equals, and I'm going to make this minus 5 meters per second squared times time squared, minus 15 meters per second times time, and then plus 200 meters. Now remember, these are units, meters per second and meters, those aren't an extra variable. So make sure that when you think of these, you're thinking about them so that they go together. They're not something that you need to replace or multiply by. All right, so I'm gonna make this a little bit simpler. I'm gonna divide each of these by minus 5. And so when I do that, I get 0 equals t squared plus 3 meters per second times time. Yeah, and this really becomes 1 meter per second squared. So that's going on in there. And then minus 40 meters. Okay. So then we're going to solve this. We've got a 1, a 3, and a 40. So remember, when we do factors for this, we're going to need factors of 40 that have a difference of 3 between them. That's going to be 5 and 8. Yay, we don't have to do that quadratic formula solver thing. Okay, so we know that we've got two quantities in brackets. The positive, we said the factors here were going to be 5 and 8. So the bigger one is going to get the plus sign because this one has plus. So plus 8 minus 5 equals 0. So this tells us that time equals positive 5 or minus 8. And those are both seconds. So which one are you going to pick? Time doesn't go backwards, guys. Pick the positive one. So it's going to take 5 seconds to go 200 meters. Guess what? If we were paying attention, that's what we calculated up here in part C. What's the displacement during 5 seconds? Well, at the end of 5 seconds, we've traveled 200 meters. Pretty cool. So if you notice things like that, your numbers should always agree. You shouldn't get different numbers just because it's a different place on your homework sheet. Okay. Lastly, calculate the speed after falling 750 meters. This guy didn't really throw a ball 750 meters, did he? No, but we're just using the equations that we know to be able to extrapolate and solve problems. So we're trying to find a final velocity after a displacement of minus 750 meters. Again, our initial velocity is equal to minus 15 meters per second and acceleration due to gravity of 10 meters per second squared. So there again, we have 3 things, so we can solve for the 4th one. In order to do that, we're going to refer to our handy equation sheet, and we're going to pick this last one with all these squared values in it. So our final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. Okay, so to get this value, which remember is going to be squared, I'm going to do our initial velocity squared, 15 meters per second squared, plus 2 times minus 10 meters per second squared times our displacement, or minus 750 meters. So to solve for this, we're going to end up with a value. Let's see, this first part is going to give us 225 meters squared per second squared. And that's because this is a value that's velocity squared. So we're going to have to do the square root of this. We're done. And then that's positive. Whoops, I dropped a sign. And that's positive because that's a negative sign there. Plus, and then this part of the equation is going to give us 1,500 meters squared per seconds squared for a grand total of 1,725 meters squared per second squared. But we're trying to find the square root of that. All right, so the square root of 1,725 meters squared per second squared is going to give us plus or minus 734.8 meters per second. Now it's plus or minus. So we have a ball that's been thrown in the downward direction. And so we're going to need to choose the minus one. So your answer should be something like minus 735 meters per second for our final velocity. Okay, so now we're going to move to a new problem. All right, now we've got a rock that's been thrown upward. This is a little bit different. So our upward thrown rock is going to have an initial speed of 10 meters per second on Earth, which again is telling us about acceleration. First, make a well-labeled diagram of the situation. Okay, so I've got a rock that's thrown upward. It doesn't say that there's any horizontal displacement. So we have something that's thrown up and then it comes back down, right? We're told that the initial speed, our initial velocity, is 10 meters per second and it's thrown up. Remember, so if this is positive, and this is negative, any vectors going upward are going to be positive. Any vectors going downward will be negative. So this one's going to be positive 10 meters per second. So there's my diagram. It says make a list of given quantities and quantities defined, label with units and appropriate algebraic signs. So for my students, the things that we already know is that our initial velocity is 10 meters per second and our acceleration due to gravity is minus 10 meters per second squared. So those are things that we already know. Down here, this first question actually says, what's the acceleration of the rock? Acceleration due to gravity is always minus 10 meters per second squared. All right. Calculate the rock's height after 2 seconds. So this is giving us two new variables. We already know initial velocity and acceleration. This one down here says figure out the height. So we're going to try to find the delta y after 2 seconds. So it's telling us that time is equal to 2 seconds. Well, now we've got three things that we know, and we're going to solve for the one thing that we don't know. In order to do that, we're going to use our quadratic equation again. Change in y equals 1/2 at squared plus vit. So 1/2 times minus 10 meters per second squared times 2 seconds squared. Don't forget to square that one. Plus our initial velocity, 10 meters per second times 2 seconds. This is going to equal these over here. 2 times 2 is 4, times minus 10 is minus 40 divided by 2. It's going to give us minus 20 meters. But then we're going to also add another 20. And this is a weird problem. Look at this. It tells us our displacement is 0 meters. What does that mean? It means that this particular rock was only thrown hard enough that in 2 seconds, it came back to the ground in that amount of time. Yeah. All right. So that's how we solve that kind of problem. Next, calculate the time required. So how much time did it take to reach an upward speed of 5 meters per second? So here it's lost half of its velocity. So we know our final velocity is 5 meters per second. So in order to solve that, we're going to use our first equation on our sheet. So our final velocity equals initial velocity plus acceleration times time. Our final velocity is 5 meters per second. Our initial velocity was 10 meters per second. Our acceleration is minus 10 meters per second squared, and we want to solve for time. So we're going to subtract 10 meters per second from both sides of this equation. So we have minus 5 meters per second equals minus 10 meters per second squared times time. So that time is minus 5 meters per second divided by minus 10 meters per second squared. So it only takes a half second for our object to lose half of its speed. All right, let's slide my paper up. Next, calculate the time required. So we're going to calculate time again to reach a downward speed of 3 meters per second. So now we're going to find time. We're reaching a final velocity of minus 3 meters per second. Our initial velocity was 10 meters per second, and our acceleration due to gravity is minus 10 meters per second squared. We're going to use the same equation that we used up here because it's the same kind of problem. Calculate the time to reach a speed. So we're trying to find final velocity again. So final velocity equals initial velocity plus acceleration times time. Here our final velocity is minus 3 meters per second equals 10 meters per second plus minus 10 meters per second squared times time. We're going to subtract 10 from both sides. So now we have minus 13 meters per second equals minus 10 meters per second squared times time. Time equals minus 13 meters per second divided by minus 10 meters per second. And so here our object is traveling downward at a velocity of 3 meters per second at 1.3 seconds. Remember, it only took 2 seconds for it to hit the ground, so this makes sense. We've got an object now that if this is 1 second, this is 2 seconds, you know, we're in here somewhere where our object is traveling at minus 3 meters per second. Okay. On to problem number 3. A ball punted vertically has a hang time of 4.2 seconds. What was the initial velocity? Make a well-labeled diagram. Make a list of given quantities and quantities defined, labeled with units and appropriate algebraic signs. All right, so what are all the things that we can know about this problem? Well, first, we need to keep in mind that we've got a ball that's punted up in the air, and it's going to go up and it's going to come back down. What we found in my class when we did a lab, we found that this happens at half of the time. So the peak that your ball travels is going to be a symmetrical path, and that amount of time is going to be exactly in the middle of the total amount of time your object is in the air, as long as the start and the end are at the same elevation. So here we know that the time is 4.2 seconds. Up at the top, we know that the time then must be 2.1 seconds. And that's something that's really important for us to realize, because we know things about that point. We also know that at that point, the velocity is 0 meters per second, which is pretty important. Sorry about that. It's early and I haven't had enough to drink yet this morning. Okay, so it's important that we understand what's going on at that point, because it helps us to be able to solve problems. So things that we know. We know that our acceleration due to gravity is minus 10 meters per second squared. We know that our total time is 4.2 seconds. We know that what I call half time, 2.1 seconds, and then at that point, our velocity equals 0 meters per second. We're asked to find initial velocity. Do we have enough to do that? Okay, so here's what we have to do. This is going to involve some strategy. If we think about this point up here, we know the amount of time it takes to reach that point. We know the velocity at that point, and we know the acceleration due to gravity, which meets our 3 things requirement. And so we can use that information to figure out how high the ball travels. Once we know how high the ball traveled, we can figure out its velocity. So that's one way we can go. The other way we can go, let's check our equation sheet. So here we can find initial velocity if we know final velocity and change in distance. Here we can find initial velocity if we know final velocity and the amount of time. So it looks like that was probably the easier way to go. So if we say, all right, final velocity equals my initial velocity plus AT, and I'm going to solve for initial velocity. I'm going to say my final velocity is 0 meters per second, because we're only focusing on this first part of this path. We're going to initialize the punt at the bottom and wait till it reaches the peak at the top. So that's 0 meters per second equals our initial velocity, the thing we're trying to find, plus minus 10 meters per second squared times time, which is, where'd my time go? 2.1 seconds. All right. So this value here is going to end up being minus 2.1. So I'm going to add that to both sides. So I'm going to say 2.1 meters per second equals initial velocity. Okay, so 0 meters per second equals initial velocity plus these 2 things multiplied together. That 10 times 2.1 is going to give us 21. So this right here should be 21 meters per second. 21 meters per second. Can we figure out what the height is? Yeah, sure. If our change in vertical displacement equals 1/2 times acceleration times time squared plus initial velocity times time, I can use this value down here for my initial velocity. So we have 1/2 times minus 10 meters per second squared times my time squared. So halfway up is going to be 2.1 seconds squared. Plus 21 meters per second times 2.1 seconds. And then what I'm going to find, if I pull up a calculator, 0.5 times minus 10 times 2.1 squared plus 21 times 2.1, and I'm going to get 22 meters. So that's how high we went. So now we know everything we need to know about that problem. All right, on to the next page. All right, next, a rock is thrown straight up with an initial speed of 25 meters per second. How long will the rock be in the air before it returns to the thrower? Graph the vertical position, velocity, and acceleration of the rock on the axes provided. Make a well-labeled diagram of the situation. Make a list of given quantities and quantities defined, labeled with units and appropriate signs. So again, we're going to try to solve all the things. And we also have these graphs. So here we know that when we have a ball that goes in the air, it's going to travel up and then it's going to travel back down. So if we're looking at the distance, it's going to move away from the point of origin and then come back down to the point of origin, right there on the ground. So over here on this graph where we have x just means position. It doesn't mean that it's moving horizontally. So, you know, I don't know if it makes you feel better. I like to put a delta y there so that I know it's a change in vertical displacement. And what that's going to look like is a parabola, right? We have something that increases in distance away from its origin point and then slowly returns back to it. All right. So if we know that, we can also use our handy slope-o-meter to figure out our velocity and our acceleration. Down here, we know that our slope of this line tells us about velocity because the velocity is equal to the change in position divided by the change in time, which is the same as the slope of this line. Change in y, change in time. So our slope down here is positive and kind of steep. And what we notice is that as we move this way, that our slope is getting less steep and approaching zero. Then our slope continues to increase in magnitude, but now it's a negative sign as our object is moving along these data points over to the opposite side where it hits the ground again. So an important reference point here is that midpoint of that path. And we know what's happening there is that the slope is approaching zero. So it's going to go through the zero line there. Over on this side, it's the highest value that it has. Over here, the slope has the most negative value that it has, but that negative magnitude is equal to the magnitude of the positive slope. So when we draw our velocity versus time graph, we're going to have a line here and here that are about the same value on either end. So we end up here. So we end up with a velocity versus time. That should be a straight line. It's kind of bendy, but we end up with a velocity that starts higher and positive, goes to zero, and then becomes negative. The slope of that line in turn tells us about acceleration because the change in velocity divided by the change in time is acceleration. We know that it's negative, and we also know exactly what value it has. So we know that over the entire amount of time that we're interested in, that this slope is constant and it's negative. And we know that the value of the acceleration due to gravity is minus 10 meters per second squared. So that's what our curve should look like, our stacks of graphs. In order to figure out the things that we know. So here we're told it has an initial speed of 25 meters per second. We also know that the acceleration due to gravity is minus 10 meters per second squared. We also know that up at this point, our velocity is equal to 0 meters per second, which may come in handy later. All right, draw a velocity and acceleration motion map for the trip. So this is two-dimensional motion, which is a little bit different than one-dimensional motion. So let's see. It says thrown straight up, so we don't have to worry about that so much. So if we're going to go straight up, I'm just going to draw my motion map straight up. It's no big deal, right? I know that I start with a velocity of positive 25 meters per second. So in 1 second, I've traveled 25 meters, but I'm going to lose 10 meters per second every second. So we're just going to make some estimates here. So 25 meters, and then the next second, I'm going to travel 10 meters. So I'm going to reach 40 meters of height. After the next, it's a change of 15. After the next one, I'm going to have a change of 5. Right, so now I'm at 45 meters. And then I'm going to slow down, right? I'll peak somewhere after 45. And then my object is going to fall back. T equals 0, T equals 1, T equals 2, T equals 3, T equals 4, not sure where that is, T equals 5. These might be a little bit off, but I'm just estimating where they are. And then I'm going to draw some arrows. My arrows are always in the direction of motion, and they're always for velocity half the distance between the two. I could just add acceleration to these. I'm going to grab a different color pen real quick. And acceleration, as we said before, is always minus 10 meters per second. So it's constant and it's negative. So I'm going to draw those arrows. They're all going to be the same length. And they're all going to be downward. Still have to see them on the backside. So my light blue lines are for acceleration. My dark blue lines are for velocity. And that's just telling me which direction I went. This problem doesn't actually ask us to solve for too much. So I'm just going to move on to the next one. All right, number 5, a student throws a baseball off a 175-meter bridge with a downward speed of 10 meters per second. How long does it take the ball to hit the ground? How fast is the ball moving? Sorry, how fast is it going at the moment of impact? One of the major misconceptions my students have is, oh, it hit the ground. It has no velocity anymore. We want to know the velocity right as the ball approaches the ground, just before it actually impacts it. So we're going to try to calculate that as a final velocity at the bottom of a motion. So things that we know. We know that our vertical displacement is going to be minus 175 meters because the student is throwing it downward, and downward is the negative direction. We also know that the ball has an initial velocity downward of minus 10 meters per second. So how long does it take the ball to hit the ground? All right, we need to know 3 things to be able to solve the 4th one. The 3rd thing that we know, again, is acceleration due to gravity is minus 10 meters per second squared. So we've got vertical displacement, initial velocity, acceleration, and how long is asking us how much time does it take? So if we look at our equation sheet, displacement, acceleration, time, velocity. All right, this looks like we need to use our quadratic again. So our change in displacement is equal to 1/2 times acceleration times time squared plus initial velocity times time. So we've got 1/2 times minus 10 meters per second squared times time squared. Again, that's our variable that we're solving for, plus our initial velocity times time. Oh, forgot to put in my displacement. I'm going to add my displacement to both sides. So I have 0 equals minus 5 meters per second squared times time squared, minus 10 meters per second times time. Again, meters and seconds are units. They're not variables. Times time plus 175 meters. And I am going to divide all of those by minus 5 meters. So that's going to remove meters from everything. So 0 equals, let's see. So 0 equals 1 second squared times time squared plus 2 seconds times time minus 175 divided by 5. Let's see, it should be, I think 35. Yeah, minus 35 with no units. All right, so if we're gonna try to factor this, 0 equals, I've got two things, time. My units here are gonna be seconds. And then, let's see, I've got to factor 35 with a difference of 2 between them. So that's going to be 5 and 7. The one that's going to be positive, because this is a negative sign here, one of them has to be positive and one has to be negative. So my positive one is going to be the 7. So t plus 7, t minus 5, which means solving for time, I'm either going to have minus 7 seconds or plus 5 seconds. Guys, you can't go back in time. Pick the forward one. All right, so it's going to take 5 seconds for the ball to hit the ground. Now imagine how high this bridge must be if he throws a baseball downward and it still takes 5 seconds to hit. It's a long time. All right, and how fast is the ball going at the moment of impact? So here we're trying to find a final velocity. We know that the displacement, the vertical displacement, is minus 175 meters. We know that acceleration due to gravity is minus 10 meters per second squared. And we know that our initial velocity is minus 10 meters per second. So to solve for this one, we're going to need, let's see, final velocity, initial velocity. Final, initial. Yeah, so we're just going to use this third equation here and solve for final velocity. I always like when it ends up that the variable we're trying to solve for is by itself. All right, so initial velocity squared plus 2a delta y. Try to mark that off there. All right, so our initial velocity, again, minus 10 meters per second squared plus 2 times acceleration times our vertical displacement. So we've got 100 meters squared per seconds squared plus, let's see, 175 times 2 is going to be 350 times minus 10. It's going to be 3,500 meters squared per second squared. So that gives us a total of 3,600 meters squared per second squared. That's pretty nice. We can do that, right? So our final velocity is equal to the square root of 3,600 meters squared per second squared. So I believe that gives us, let's see, I believe that's 60. Just going to double check. Nothing wrong with double checking our math. Yep, and I got 60 meters per second. That's our total. All right, there's another way we could solve this problem. Most problems have multiple ways you could solve them. The other way that you could do it is we could say, well, you know, we figured out that it took 5 seconds for it to hit the ground, and nothing about this was different than this situation. So if we say, well, what if I know that my time is 5 seconds? Does that mean I can use a different equation? So if I look up here, I could use this first one, which I think is a lot easier because it doesn't have anything squared in it. So if I have my final velocity equals initial velocity plus acceleration times time, my initial velocity is minus 10 meters per second. And then I'm going to add that to my minus 10 meters per second squared times 5 seconds. And check this out. You end up with minus 5 plus minus 50. And it's the same minus 60 meters per second. Oh, wait. Remember, guys, this is square root, so this is going to be plus or minus, right? So if this is plus or minus, we're going to need to make sure that we choose that negative minus 60 meters per second. But see how those two match? If those didn't agree, we might have an issue. It might mean we calculated our time wrong. So if you were up here and you switched your signs when you were doing your factoring and you chose the 7 seconds, you wouldn't get the same answer here. And that would be a tip that something had gone horribly wrong. All right, I think we have one more. Sorry, I have lots of paper shuffling around. So our very last one. When a kid drops a rock off the edge of a cliff, it takes 5 seconds to reach the ground below. So we need to have a cliff. Let's draw these cliffs with kind of a hangover there. It reminds me of Red River Gorge. It's a great place to hike. All right, so a kid drops a rock off the edge of a cliff. So there's the rock, and it's falling. This is whooshy marks behind it, so that's how we know it's falling. And it takes 5 seconds to reach the ground below. When she throws the rock down, it hits the ground in 4 seconds. So if we throw it, it has longer whooshy marks, right? So here our velocity is 0. For this one, our velocity is unknown. We're going to have to calculate it. It hits the ground in 4 seconds. So we have a 5-second situation and we have a 4-second situation. So this is faster. So it's got to have some initial negative velocity. All right. What do we know? We know that the acceleration due to gravity is always minus 10 meters per second squared. We are also given 2 different times. So for this one, when time equals 5 seconds, the initial velocity is 0 meters per second. Oh, look, we know 3 things. So we can solve for something else. Well, what will be useful to know? The thing that would be really helpful for us is to know how high this is. So our change in vertical displacement is equal to 1/2 AT squared plus VIT. Easy enough. So 1/2 times minus 10 meters per second squared times time, which is 5 seconds, plus our initial velocity, which is 0. So we don't even have to worry about that. All right. Have to be careful about forgetting that squared there. So that's going to be 25 times 10 is 250 divided by 2 gives us minus 125 meters. So when this object falls, now we know that this distance, let's see, I'm going to write delta y equals minus 125 meters. So now that's a thing that we know. So for the second part, the speed for what the student gave the rock, we know that time equals 4 seconds, that the displacement is minus 125 meters, acceleration due to gravity is minus 10 meters per second squared, and we're going to find initial velocity. Looks like we're using the same equation here, folks, because we don't know final velocity. If we knew final velocity, we could use this first equation, but we have to use the second one because we don't know final velocity. So both the first and the third equation here are out. No good. Can't use them. So our displacement equals 1/2 AT squared plus VIT minus 125 meters equals 1/2 times minus 10 meters per second squared times 4 seconds squared plus VI times 4 seconds. It's a lot of things to do here. Okay, minus 125 meters equals 4 times 4 is 16 times 10 is minus 160 divided by 2 is minus 80 meters plus VI times 4 seconds. If I add 80 to both sides, I'm going to end up with minus 45 meters equals VI times 4 seconds. So my initial velocity equals minus 45 meters divided by 4 seconds, which is going to give me it's about 10, right? .25 meters per second. Pretty cool. All right, guys, so when you're doing problems like these, make sure that you're maintaining some good habits. One thing, it's really important to keep track of things like which variables you already know, because if you ever know 3 of them, you can use any of these equations to solve for things, and that's really helpful. I hope that helped you. If you have any questions, you can try to reach out to me. I hope you have a great day. Stay safe and be well. I'll see you soon.